Hey class, in this video we will be talking about test of significance, and in this intro video I wanted to just talk a little bit about how evidence, and I put this in parentheses in the title, is done with statistics. Because as we've been talking about the last couple weeks of class, you can never prove something is true or prove the value of something that we don't know using statistics, but like with chapter 16 on confidence intervals, we can create an interval that is likely to include the correct value for a population parameter. And chapter 17 is very similar. I've alluded to the fact that the math is exactly the same, just how we use it is a little bit different. And essentially it's kind of let's get into it in the next couple of videos. But just a couple quick review recaps, because those are important for math in chapter 17, is remember that when we draw a sample of data from the original population, the standard deviation changes depending on the sample size, meaning that a larger sample is more likely to be correct than a smaller sample size. And the standard deviation reflects its probability in the normal distribution, because remember, when it's a smaller standard deviation, it's more packed together, and those data points that we draw from there are more likely to be accurate. And all of that is emphasized by the central limit theorem. And we can often use normal probability calculations to predict, essentially, say, again, the idea is that we don't actually know the true value of a mean of, say we're trying to look at college students, so we want to know what's the average age of PLNU students. If we draw a sample size of 100, we're unlikely to get exactly the right answer. But what we do know is that sample will follow a normal distribution, and the standard deviation of that sampling distribution will be dependent on n. And we can use probability from the normal distribution to figure out those problems. And with confidence intervals, we were working on this last week in class. It boils down to a formula, which we talked about kind of the meaning of why, but essentially it's like when we take a sample, that's the best guess for what the value we're trying to obtain, mu. Mu is the mean of the population. X bar is the mean of our sample. And it's an unbiased estimator to the true value of the population. But since we know this is unlikely to be exactly right, and we also know the data follows a normal distribution, what we can do is expand the range in terms of a confidence interval. And we know exactly the probability that the true value of the parameter will be within that interval based on the normal distribution math. So just remember that Z star is called a critical value. It's what we can look up in a t-table or table C in the back of our book. And then it's multiplied by just the standard deviation of the sampling distribution. And all of that is designed to give us an interval of values that is some confident level of being correct. So remember, C is the confidence level of the distribution. Say we want to be 90% sure or 95% sure. We can be as sure as we want based on the expansion of that interval. So all of that being said, what is a test of significance? That is something that's different, and that's the goal of chapter 17. And we're going to start on this lecture this week, and we'll do some more problems when we come back after fall break next week. But the goal is very different. So the goal of a confidence interval is to take a statistical sample and try to figure out what does this mean about the actual population. Because again, say we obtain an X bar, we don't know if that's right, but we want to give some confident level. And the sort of conclusions we get from confidence intervals are something like, based on the sample that I've obtained, I am 90% confident that the actual parameter of the population is somewhere between here and here. And that's cool, and it's useful to provide a range of likely values for what we're trying to figure out. So a test of significance is very different, because it's kind of backwards in my mind. The goal is to gather evidence and see if what that says about the claim about a population parameter. So usually how it will work is, say we're trying to test to see whether this medication is actually effective, and we want to know, is there enough evidence to prove that this is not effective? And this is a lot of times how statistics are used with in the field of the sciences, is to really figure out, can we conclusively prove something, right? Because the issue in, say, medicine is that if we develop a drug and we do a sample trial of the drug, obviously we can't test the entire population that we want to cure. We can test a sample, and ideally we get good results, right? But again, that sample does not prove it will work on the greater population, especially if the sample has some biases or other issues. And people do a lot of unethical things to create data that is not necessarily accurate for their pharmaceutical too, but that's beside the point. But anyways, the kind of what we're looking to say at the end of a test of significance, based on my sample, this claim is true or false based on probability. It's kind of similar where we're going to want to, instead of trying to develop an interval of likely values, we're trying to say, well, here's the data I obtained. This shows good evidence that this other claim is true or false. Well, again, you can't actually prove something's true, as I've alluded to. But let's get into example one. So on your packet, and you can write this on your notes, is the goal is to assess the evidence provided by data about some claim concerning a population parameter. So let's just throw out an example number one, and then we'll be working on example two in the next few videos. But I'll just go ahead and read it. It says, Professor Havens claims that he gets a strike on his first throw in bowling 70% of the time. To test his claim, you ask him to throw 2 full games, let's say 22 throws, to see how many strikes he gets. So, this is something you can probably relate to, where your friend lies about, I'm this good at this sport, I can make 90% of my free throws or whatever. And so you say to them, well, your claim sounds suspicious. I don't really believe you. So in order to test, this claim, go make 10 free throws or whatever and see, what's your percent score. But the problem is, one question that we have is, well, say we ask our friend to shoot 10 free throws, and let's say he makes 9 out of 10. Is that good enough evidence to support his claim that he's a 90% free throw shooter or something? So, like in this example, let's say you put me to the test. My claim, or my statement was that and so I'm using the term claim carefully, because this is very easy to get mixed up on what the claim must be. And we'll talk about this in a future video on null and alternative hypotheses here in a minute. But what Professor Havens says is that he has a 70% strike rate. And let's say that you're a little suspicious. You don't think Professor Havens can actually throw a strike 70% of the time, so you want him to put him to test. So your claim would be that Professor Havens' strike rate in bowling is actually less than 70%. So this is kind of the parameter that's in question, and this we would call mu, because it's kind of like the theoretical actual average rate of strike for a professor. Now, if we actually do a sample, so we could collect some data. Let's say we throw 2 games, and let's say in my first game of bowling I bowl 5 strikes, and then in my second game of bowling I get 3 strikes. And just the total, if you don't know what a game of bowling is, that's fine. Let's just say that I throw 8 strikes out of 22 in those 2 games. If we do the math on that, right, 8 out of 22 comes out to about 36%. That is nowhere near 70%. And this is the point of the illustration, is the claim was that the true value of the strike rate of bowling was 70%. And we wanted to see if there's evidence against the claim or not. And actually, so with a null hypothesis, this is what's called a null hypothesis, and there's always a statement of equality, a statement of the true nature of the mean of the population at hand. In the counterclaim, usually what we're trying to figure out is this wrong or not? Do we have evidence that this is false? Or and this can come in a couple forms. Do we want to check to see if Professor Havens' strike rate is lower than 70%? Maybe we think it's higher than 70%. Maybe we just think it may be either lower or higher, but it's not that. And these are what are called one-tailed and two-tailed tests. We'll get back into this a little bit later. But what you can tell in this case is that these are very different. This is strong evidence that Professor Havens does not have a 70% strike rate, because his given evidence displays a much different result. And so we actually want to do math, though. In this case, it's pretty clear that Professor Havens' strike rate may not be 70%, but maybe he just had a bad game. Maybe the lanes were terrible. Who knows? This is never proof that Professor Havens can't throw a 70% strike rate in bowling. It's evidence. And this is why this video is all about, what does statistical evidence really mean? In this case, we can use binomial distribution math to actually calculate, what's the probability that Professor Havens would do this bad, 8 out of 22 strikes, if he actually had a strike rate of 70%. And all of this math was in chapter 13, I believe, to which is not part of our curriculum, and we're skipping over entirely. So these numbers, they won't make sense why they're true. But essentially, what I did is I graphed out what's the probability that Professor Havens threw no strikes out of 22, 1 strike out of 22, 2 strikes out of 22, and so forth, all the way up until probability, let's say, of throwing 22 out of 22 strikes, which is also unlikely. And all of this information was predicated on the claim. We always assume the claim is true, and we want to essentially not prove, but demonstrate that it's false by showing it's so unlikely. And in this case, if we add up all of the probabilities, so what this, each one of those would be the probability that Professor Havens threw that many strikes out of 22. And so the evidence that we gathered, right, was that Professor Havens struck 8 times out of 22, which that specifically has a 0.09% probability. Very, very unlikely to happen. Again, assuming my strike rate was 70%. And, similarly, let's say Professor Havens could have bowled less strikes. He could have been worse. He could have thrown 7 out of 22, 6 out of 22, 5, and so on. If we add up all of those probabilities, it comes out to a total percentage of about 0.1% that I would throw either 8 or less strikes. So essentially, the math shows that the likelihood of Professor Havens bowling 8 or less strikes, basically the probability of me bowling this bad, if I actually have a 70% strike rate, is less than 1%. It's actually 0.1%. Basically, one time out of 1,000 would I bowl that bad if the claim was true. And all of this is kind of leading us to the conclusion that this is so unlikely that this should convince you that my original claim is false. Essentially, 70% strike rate is very unlikely because in Professor Havens' demonstration of his strike rate, he did not, live up to those expectations. Now, let's say I got like 13 out of 22 strikes. That is a lot lower. But if we continue on our probability, 9, 10, 11, 12, 13, there's about a 10% chance that someone who has a 70% strike rate would only throw 13 out of 22 strikes, which again, that's really not, I say only, but 13 out of 22 is pretty good. And, if we add up all of the probability, of that happening, of excuse me, either getting a 13 or less strikes, if we, just doing a little bit of rough adding, that's going to look like something like 14% or 13, 14%, whatever that may be. But that may not be strong enough evidence instead. But, very, very, in this case, it was super unlikely that Professor Havens would bowl that bad. And so we can conclude his claim is most likely false. And, to summarize this video with a good quote, this is an outcome that would rarely happen if a claim were true, is good evidence that the claim is not true. And this is kind of the idea in a test of significance. Now, in the next few videos, I'll try to teach you guys, how do we actually formalize this process. There's a lot of terms and stuff that will make it a little easier so that if you're the type of person who likes to, follow the rules and, do this, then this, then this, we can create a very procedural way of going about this. But these problems are typically complicated just due to all the logic of how a test of significance works. And we'll pick this up in the next video.